Hi all! Today let's talk about recursive functions. Although some of us have never heard of recursive functions before, we have seen them many times. A classic example of a recursive functions in mathematics is factorial. In order to calculate 5 factorial, we must calculate 5 times 4, then times 3, then times 2, then times 1. Here you find yourself doing something again and again, or put it another way, recursively. And voila, you have a recursive function. If you type recursive function in Google image, you may run into something like this. Annoying as it seems, this is actually what recursive functions look like, with layers inside layers, and each of these layers is one time a function is called. Now, let's recall that any function may take in inputs and produce outputs. Recursive functions are no different. What's even more interesting about a recursive function is that it will keep on taking inputs if there are any, every time it is called until it stops calling itself, which means it has reached the innermost layer. Then the function starts producing or returning outputs, if there are any, until it gets out of all layers. So, how does a function know that it has reached the innermost layer? We call the 5 factorial. How do you know when you should stop taking productive numbers? You stop when you reach the number 1, right? It's the same for a recursive function. It knows when to stop calling itself when a base case or a special condition is met. In the case of 5 factorial, a special condition is the number 1. Let's have a look at an actual recursive function that I wrote to calculate the factorial of a number. In this program, the recursive function is defined at the end. We know this function is recursive because we see the name of the function inside itself. As you can see, there are two cases with if and else conditions. Those are the base case and the recursive case. In the base case, the function returns a specific value without calling itself. We immediately know what the return value will be. Here, factorial 1 and factorial 0 equals to 1. Only when the base case is not met does the function execute the recursive case, where it calls itself before returning something. We cannot know immediately what the return value is and must keep on calling the function until we reach something that we know, which is factorial 1 or factorial 0. So let's see how factorial 5 works. Since 5 is equal to neither 0 or 1, this function will skip this if condition. Now it hits the else condition, but in order to return an output, it must first know what factorial 4 equals to. This is where the function calls itself, and this is where we enter a new layer of recursion and repeat the same steps. In order to calculate factorial 4, we must know factorial 3, factorial 2, and factorial 1. Now we already know that factorial 1 returns 1. This is where the function stops taking input and start producing output. We move out of the layer factorial 1 and back to layer factorial 2. The output of factorial 1 is used to calculate factorial 2 and so on until we finally calculate factorial 5. So up to now, recursive function seems to be a perfect solution to problems that are inherently recursive like factorial. However, it does have its own disadvantage. Recall that every time a function is called, a chunk of memory in the stack is assigned to that function. As factorial is a recursive function, it will require a lot of chunks of memory. It is okay if the recursive function only calls itself a few times, but if we don't have the base case that tells the function where to stop, or if the function tries to call itself too many times, soon the stack will be filled and we end up with stack overflow. So that's all we need to know about recursive functions today. Here's a brief overview of what we've covered, and I hope that you understand recursive function now. Bye!